As we talk about biology and the origin of life, it's good to start at the beginning. And the beginning of the history and time of the universe is the Big Bang. And the theory of the Big Bang explains how the universe is here today and why it is the way that it is, why all the laws of physics exist, and why time and space act the way they do. And of course, the theory of the Big Bang says that everything there ever was in one spot, in a singularity point. All the energy, all the matter in one small spot. And that was so dense and so hot that it exploded and expanded very, very fast. And then at first, all you form is these small subatomic particles like quarks, and eventually those quarks organize themselves into bigger and bigger elements, and then the elements form clouds of gas that will go on to become protostars and protogalaxies. But this theory has a lot of detail and a lot of evidence collected over hundreds of years of research and astrophysics and astronomy and earth science and earth space science that it's not the class that we're teaching right now. So what I want you to know about this is that the theory of the Big Bang explains the origin of the universe. And I want to do a brief review of how we get from there to the conditions of the early Earth where life was actually going to begin. So again, the Big Bang explodes, and then from that point, you're going to have the formation of the first particles, the first atoms, the first elements, the first pockets of glass, and then those gases will actually coalesce themselves through gravity into young stars and young galaxies. And one of those young galaxies was the Milky Way. And in the little corner of the Milky Way, about 2/3 or 3/4 of the way out, you had a little pocket of gas, a solar nebula, that coalesced itself through gravity, agitated by a solar event such as a supernova. And that mass became more and more coalesced, and as the gravity brought the gases closer and closer together, they got hotter and hotter, and eventually would ignite into fusion to form what it is today, the Sun. Meanwhile, on the outskirts of the Sun, disks of matter that never coalesced inside of the star actually form other secondary disks, which will become the planets. And these disks were full of debris and gases that gravity brought together into other small blobs of matter that we called protoplanets. And these protoplanets gathered more and more matter through gravity, collisions between meteors and comets and pockets of gas, and eventually the protoplanets got larger and larger. One of these protoplanets, in a little corner, 3 planets down from the Sun, was the Earth. And as the Earth went through repetitive collision events like this, it eventually cooled down as it cleared more of its orbit, and then it became the early Earth that was a blob of fire cooling down more and more. Early in that process, Earth was actually hit by a massive Mars-sized object that tore a whole chunk of the Earth out, and from that chunk, that would start to orbit the Earth and eventually would become the Moon. And that's how we get our planetary system with one planet surrounded by one moon. But over time, the Earth would actually cool down, and so would the Moon, and form layers, differentiated layers, where the heavier elements will fall towards the center, and then the lighter elements will stay towards the top, and form 3 different layers: the Earth, crust, the mantle, and the core. Today, the inner core is actually solid, compressed by all the gravity that's around it, but surrounding that, you still have a molten rock, just like Earth was in the beginning, because the core is so hot. Then you have the mantle, which is kind of molten, kind of not, and then you have the solid, brittle crust on the outside, shattered by the heat of its inside in the process of plate tectonics. As the Earth cooled down, you also have the development of the geosphere, the atmosphere, and the hydrosphere. I just described the development of the layers of the geosphere and the fact that these layers are constantly under pressure from the core, and that's what causes things like plate tectonics and deformations of the crust, which explains all the structures of geology of the Earth. And if you're interested in that, watch my lecture series on the geology for Earth-Space Science class. Now, at the same time, you have the formation of the hydrosphere of the Earth and the atmosphere of the Earth. The atmosphere of the Earth forms through similar processes. Volcanic eruptions put gases around the Earth which are trapped by the gravity, and these gases form a layer of gas, a little pocket of gas that surrounds the planet. Originally, these gases were mostly toxic gases that come from the volcanoes, like hydrogen-rich gases, helium-rich gases, carbon dioxide, methane, ammonia, and other gases like that. But these gases will form a pocket that will eventually rain down. Water vapor, by the way, was also one of those gases. Water also came to the Earth through comet strikes, because comets are rich in water. Lots of the comets have a lot of water. Successive events like volcanic eruptions and comet strikes made more and more water gather around the Earth and eventually form the early oceans. Now, this process will continue over millions and millions of years, and eventually the oceans will gather more and more from comet strikes and volcanic eruptions full of water vapor, which will gather in the atmosphere and rain down with all the toxic fumes of methane and other things like that. Meanwhile, the light gases such as helium and hydrogen, which are very light and not so easy to trap with gravity, got blown off by solar winds into the outskirts of the solar system and probably absorbed by planets like Neptune and Jupiter and Saturn and things like that. Meanwhile, the atmosphere of the Earth will become more carbon dioxide and nitrogen rich as these other lighter gases got blown away by the solar winds. So that's how the atmosphere of the Earth goes from an early atmosphere rich in hydrogen and helium to an atmosphere rich in things like water vapor, carbon dioxide, and nitrogen gas. Especially nitrogen gas, which is heavy enough to be trapped by the gravity of the Earth. Remember, at the same time, the hydrosphere is forming through comet strikes and water vapor coming from those volcanoes. So the atmosphere of the early Earth was a lot more rich in water and carbon dioxide and methane and ammonia and other gases like that. But as those gases got pushed out, nitrogen became the most common thing. And oxygen would not become a common part of the atmosphere until much, much later after life evolves and forms photosynthesis. And the process of photosynthesis makes the atmosphere become more oxygen rich. That is actually a very important point as we talked about abiogenesis, because if the atmosphere was rich in oxygen in the very beginning, life on Earth in the process of abiogenesis would be impossible. Because the thing is that abiogenesis requires an atmosphere that does not have oxygen in it. Oxygen is actually an oxidizing agent, which actually causes a lot of problems in the chemical reactions necessary for life to start. But that's okay, because on the early Earth, we probably didn't have that much oxygen. And we're going to talk more about that later. But if you're interested about these processes of the formation of the hydrosphere, the atmosphere, and the geosphere, watch my lecture series on Earth-based science and learn more about it. But what you need to know is that a whole story of the universe happened all the way before the story of life actually starts. By the time life on Earth started, the universe was already 10 billion years old. So you already have a very old universe. And the Earth itself is also very old. The Earth is going to be about 1 billion years old almost by the time the first life form shows up. By then, the Earth already has an atmosphere which is rich in nitrogen, more so than the methane and ammonia. The light gases have already been blown out. The volcanic eruptions are already slowing down. Plate tectonics is becoming the way it is today, slowing down. And you also have an Earth that's no longer molten. Oceans are becoming more and more deep as water accumulates from volcanic eruptions and comet strikes. The strikes are actually slowing down, and you're going to have less and less astronomical events. And as time goes by, you have these conditions for the early Earth, which we'll discuss in the next video. I'll see you guys then.